So it is lecture number 3. And we will discuss ordinary and singular points of the points of the differential equation, of differential equations. Okay. We will start to discuss some, to consider an example, and using this example I will try to explain the problems that arise in this way, right? And the necessity to introduce the notions of an ordinary and singular point of a differential equation, right? And we will start with the example. Let it be here. We will consider a differential equation y equals it is equal to 2 y minus 1 over x. Okay, of course x should not be equal to 0. So this is a differential equation defined on this interval. So it is the entire real line except for the origin. Okay, and try to investigate this differential equation and its solutions. So we will, of course, we can of course solve this differential equation explicitly. But first of all, so since we want to discuss the geometry of this, the geometric effects of these differential equations, I will start with integral curves with the geometric approximations of solutions, right? So geometrically, we start with the geometrical analysis. Geometrical analysis of this equation. So first of all, so we start with the direction field. So let's construct the direction field. So what is that directional field? Do you know? Direction field. So what is it? Okay. So do you know what line element is? Line element. No. Okay. So I will repeat maybe. So given, I will use this space. Given a first order differential equation. So sometimes, and it may happen very often that it is impossible or very difficult to obtain the explicit solution of this differential equation. But we may analyze, we may study the geometry of this differential equation, and we may construct a geometric approximation of a solution using the following technique. If we fix the point, so suppose we fix a point x0, y0, where x0, so the differential equation is usually given in some interval I. So this means that x is between a and b, some points a and b. So we will consider this differential equation on an interval. So x0 is in this interval, and suppose this function is defined for these particular values of x and y. So it is defined. Then we can compute this value. So we can compute f of x0, y0. and this will be the slope of an integral curve, right? So an integral curve is a graph of a solution of this equation. So if we imagine that we can solve this equation explicitly, so if we have an explicit solution, then the graph of this solution is called an integral curve. Suppose it looks like this curve. Suppose this is an integral curve, and we can see that at each point x0, y0, the tangent line to this curve has a slope which is equal to this function. And so if we can't find this function, if we can't solve this equation explicitly, we can so in any case we can find the slopes at every point, because we can substitute values x0 and y0 into this function. This function is given, and we can compute the exact value of this function at this point. And so at each point we know the slope. We know a slope, right? And if we want to solve this equation geometrically, so to find geometric approximations of this of solutions, right? At any point we can construct slopes, right? So to substitute these coordinates into our function and find the slope. And so we will have the direction field, which consists of these small line elements. So this is called a line element. So a line element is some small small interval of a straight line with a slope defined by this function in general, right? So let's try to do to proceed with this construction for our example, right? In our example. Okay. And to so the problem is that it takes time to compute slopes, to compute these line elements, the slopes at any point. But to do this a little bit faster, we may use isocyclines, right? What is an isocycline? Do you remember? Right, the curve with the same slope, right? So if we are given this function, we may draw a curve f of x y equals k. For example, so it may be a line or maybe some curve. Construct a curve, and at each point of this curve, our line segments will have the same slope, which is equal to k. Right? Okay, and let's do it here. So we have this equation. Let's construct isocyclines. Isocyclines will have the equation, the following equation: 2 times y minus 1 over x equals k. This is an equation for an isocycline. Then let's solve it for y. And we will get the following: y equals k half x plus 1. I think it's this, right? So this is an isocycline. So all the isocyclines are straight lines, and all these straight lines pass through the point. Through which point? This is a pencil of straight lines. They all pass through the point. What is the point in common of all of these straight lines? X equals 0 and y equals 1. 0, 1 is a common point. So all the isoclines, so I will enlarge the scale. So it is 0, it is 1, x-axis, y-axis. So all the isoclines have this form. And these are isoclines. Okay, and now we need to construct line elements, right? Line elements. Okay, what about the horizontal isocline? What about line elements on the horizontal line? So for the horizontal line, we have k half is equal to 0. So k is 0. So on this horizontal line, all the line elements will be horizontal. Right. So let's consider this line. So let it be y equals x plus 1. This one. What about the slopes on this isocline? So if the slope is 1, then we have k half equals 1. Then k equals 2. So on this straight line we have something like this. These are line elements. We should continue here in the same way. Well, and next this isocline. So we have something like this. So not vertical, but so this. Okay. Okay, something like this. Okay. Okay, the question is, we can construct line elements and directional field for so line elements at any point. Is it true for any point or not for any point in R2? Are there any point at which we can't construct a line element? So we can do this for any point except for points of the y-axis. For x equals 0, we can't substitute x equals 0 into this equation, and we can't construct line elements on this line, straight line. Okay, well, and now let's, the next question, let's try to find the geometric approximation of the integral curves. Try to solve this geometrically. Try to find the curves, right? The curves that will be tangent to these small line segments geometrically. How to do this? So suppose we want to follow this streamline. So let's start with this point. Then we should move this way, and then the slope will become more horizontal, right? These line elements will become more horizontal, and so we will go to this point, right? So if we start with this point, we will go close to the point 0, 1. So we can see that starting with any point, we will come to the point 0, 1. So this way, and this way, and this way, and this way, and this way. Right, all the parabolas, right. So, but let's okay. Let's discuss the integral curves and the solutions of this differential equation. Okay. So suppose we try to maybe to improve to so we can see that all the integral curves go to the point 0, 1, but our function, our right-hand side, is not defined at this point. But maybe if we define if we define the derivative of y at this point by the value 0, maybe this will improve the situation. Then will help us to make the integral curves continuous at this point. Okay, so let's improve our differential equation by setting by doing the following. Let it be 2 times y minus 1 over x if x is not 0, and 0 if x equals 0, and y equals 1. Okay, in this case, we can see that integral curves can be so extended to this point. And suppose we start with some point, this point maybe, right? And move along the integral curve following the streamline, right? So we go here, and then we come to this point. But if we want to follow the streamline after this point, so which streamline should we choose? Which curve should we follow after crossing the point 0, 1? What is your opinion? So this way, or this way, or this way? So the answer is it is impossible to decide. So we can't choose the direction directly, the curve so correctly, right? Because so we can choose any curve after this point. And so in this situation, we can see that if we consider a point which is so whose x coordinate is not 0, then we can, if we consider a neighborhood, a small neighborhood of this point, we can see that there is a unique, a unique integral curve passing through this point. But if we consider the point 0, 1, there are infinitely many integral curves that pass through this point. So if we allow the derivative to be equal to 0 at this point, then infinitely many integral curves that pass through the point 0, 1. And if we consider points, the points for which whose x coordinate is 0 but y is not 1, then there are no integral curves passing, so crossing these points, right? No integral curves crossing these points, infinitely many integral curves crossing this point, and a unique integral curve passing through this point. So this defines the difference between, so there are several types of points. Some of them are ordinary, so these points will be called ordinary, and these are singular points of a differential equation. Okay, before I give the exact definitions of these notions, I will show the exact solution of this. So this differential equation can be solved explicitly, because this is a separable differential equation, and we can solve it explicitly. Let's do it, right? Let's do it. So let's separate variables and represent this as dy over dx equals 2 times y minus 1 over x. Then separate variables, and we will get dy over y minus 1 equals 2 dx over x, and then integrate. So y equals 1 is a particular solution, of course. It is a particular solution. You can see a horizontal line. This is a particular solution. Right. And let's integrate. And we will get the following. Ln y minus 1 equals 2 ln x plus c equals ln x squared plus c. So just a moment. Next, we will remove ln by doing the following. Equals e ln x squared plus c. This is the same as y minus 1 equals x squared times c, where c is a positive constant, right? And then y equals, if we remove the absolute value, we will get the following: c x squared plus 1, where c an arbitrary constant. And if c equals 0, then this particular solution will be included. So is any real value. So is it correct that the solution of our equation is this one parameter family of solutions? It seems to be this, but it is not correct. It is locally, so it is correct locally at the points x that are not equal to 0. But if we have, if we want to to construct an integral curve globally, so we should say the following. So we should separate this into two parts. So y equals c1 x squared plus 1 if x is less than or equal to 0, and y equals c2 x squared plus 1 if x is greater than or equal to 0. So an integral curve should be constructed of two parts, should consist of two parts. So this means that if we start from one point, right, from some point here, right, we should choose maybe this way. We can compute c1, right, by substituting the initial values into this equation. We will find c1, and if we follow this streamline, we will come to this point using the parabola, right? Following the parabola, passing through this point, right? So this is the part of the parabola, the branch of the parabola. We come, so we come here, and then after this point, we can follow any other branch of the parabola of, so we can follow any other parabola, right, given by this equation. So C2 may be different from C1, and it may be negative. If C2 is negative, we will go this way. If C2 is 0, we will go this way. And all of these paths so can be chosen, and they are correct. Okay, so an integral curve, if we consider an integral curve, if it starts here, then it may be continued in any way. So this example shows that even if we have the first order differential equation, the general solution of this first order differential equation may include maybe not only one parameter family, but it may consist of two one-parameter families of solutions. Right? It may be this equation for x, which is less than 0, or less or equal to 0, and this if x is greater than 0.
So this gives us all the integral
right. Because we can use this equation only for x which are greater than 0 or less than 0, because our computations here have some singularities at the points x equals 0 or y equals 0, because, so look here, we can't substitute one for y because the logarithm of 0 is not defined, right? And the logarithm of 0 is also not defined. And so all these computations can be conducted only only for positive axis or negative, but not 0. We can't cross the vertical, so the vertical line y, so x equals 0, right? And so all our computations are conducted far from 0, right? So in this domain or in this domain. So be very careful with this, and I want to complete this example with necessary definitions. I will introduce the notion of an ordinary point and a singular point of differential equation. So all these points will be called ordinary points and singular points. So this is a singular point, and this is the second type. So the other points on y-axis will be singular points of the other type. Okay, I will not remove this, so I will use that space. So I will give a definition. So an ordinary point of a differential equation, okay, is a point in the plane. So of differential equation of the form y prime equals f of xy, where x belongs to some interval I, is a point xy in the plane which lies on a on a unique, so on one and only one. Okay, it's better on one integral curve. and next a singular point. Is a point x, y in the plane. That meets two requirements. So the first requirement, this point is not a singular point, is not an ordinary point. It is not an ordinary point. Okay. This means that it lies on infinitely or on more than one integral curves, or it lies on just a moment, I will formulate. So it doesn't lie on any integral curve. So this means that it is not an it doesn't lie. So just a moment. So just a moment. Any notation. So on any integral curve, or it lies on more than one integral curve. Okay, but this requirement is not sufficient. So we must eliminate extraneous points. Okay, so we want to eliminate points that are far from our integral curves. So this means the following. So first I start with the example, and then I will finish the definition, complete the definition. So the following example. Suppose we want to consider the following differential equation: 1 minus x squared, maybe. Okay, the right-hand part of this equation is defined for x that are between -1 and 1 only. Right? It is defined only in this domain. But what about these points? What about the point, for example, x equals 3 and y equals maybe 2? Is the point 3, 2 singular or not? So we don't want this point to be singular because it is far from our differential equation, right? So not all these points are singular. All the singular points should be close to ordinary points. So the definition says that in any neighborhood of the point that are called singular, so this, for example, this one, there should be ordinary points. So if we draw a circle with sufficiently small radius, there should be ordinary points in the interior of this circle, right? So this can be formulated as follows. So it should be, it is a limit point of ordinary points. in any sufficient small neighborhood of this single point should be ordinary points. Okay, so this completes our definition, and so that's all maybe with this part of the lecture. And next, I want to introduce, or maybe, so we may include this part into the seminar. So next, today we will solve first order linear differential equations with non-constant coefficients, right? And I will describe two methods of solving these equations, but maybe we will do this on the seminar. Let's have a break.